So here's our first guy in 15.9. It's called part B because we had to split it up because we didn't have time to finish. You want a double integral over some region R of a function of x and y, and R in this case is enclosed by these various straight lines. So question 1 and question 2 are very similar to this. So I'm only going to do question 1 as a kind of template to these types of questions. Well, what we're going to have to do here in step 1 is find a U and a V. Basically find your U-subs, but in 2D. Now there's quite a few overlapping clues here. The region R is described by these 4 lines. Can you imagine 2 of the lines go that way and 2 of the lines go that way? So what you end up with is some kind of rectangular on its angle kind of shape. That's what these would generate. So what we need to do is we need to find a U and a V. And I said there's 2 kinds of information. It's definitely a clue is here, and that same clue is over here. Sometimes one is better than the other, but would you agree that it would be a reasonable assumption that if I made this the U and I made this one the V, that I would be able to convert from X, Y's into U, V's in the simplest form? Are you comfortable about why I chose these 2? One for U and one for V. And does it matter who you call U and who you call V? No, it doesn't matter. As long as one of them's this guy, one of them's that. How do I know it? Well, do you see these 2 guys here? Don't they just become U equals 0 to U equals 5? Do you see these 2 lines here? These become V equals 4 to V equals 5. So that means I can now tell you what the new region S is. Oops, where is my little guys? Let me find things when I want them. There it is. You've got a region R with X's and Y's. You're going to change it to a new region S using U's and V's. That's basically the way this is going to work. So S then, the region R in UV space, is simply just going to be U between 0 and 5, and V is going to be between 4 and 5. Are you happy about how I chose my U and a V? And step 2, how I found out what the new region S is. Any questions? Are we good? Right. So step 3 then. I'm going to find that guy. Now, I could find this guy, and sometimes I have to do it this way, is that I have to take these 2 equations and I have to solve them so that eventually I get X equals some function of U and V, and then Y equals some function of U and V. But I only force myself into doing that if these 2 substitutions are not linear, right? These are linear. And when they are linear, we can do a kind of little cheat, can't we? Because what we can do is we can find this fella. And this answer, when you take its reciprocal, will be this guy. Secondly, when it's linear, this answer will be a number, right? So let's see what this looks like. It's the partial derivative of U with respect to X, and then with Y, and the partial derivative of V with respect to X, and then with Y. Okay, you differentiate this with X, you get 1. You differentiate this with Y, you get -5. You differentiate this with X, you get 8. You differentiate this with y, you get -1. And this guy becomes major diagonal 1 times -1. Take away minor diagonal 8 times -5. That's 40. That is 39, I believe. That makes this guy 1 over that. And that's how I found the Jacobian without needing to do extra algebra and convert the u subs into what x would be in terms of u and v and what y would be in terms of u and v. And the only reason I would need to do that would be to find the Jacobian, right, this fella here, where the terms are not linear. So if the expressions are just, you know, multiples of x added, subtracted to multiples of y, then you can do this shortcut. So we now have this fella. So we kind of have almost all the pieces then. So what do we do next is, well, oops, put my other examples out of the way for a minute, is that we put the package together. And them just arrived. Let's see what we get. So the double integral of region R, which is 5 lots of x take away 5y over 8x take away y dA, becomes the region over S. 5 is still 5. X minus y is u. 8 minus xy is v. That's that bit. The Jacobian, which is 1/39. And then we can do du, dv. And since I know the limits for u and v are, what's v? V goes from 4 to 5. And u goes from 0 to 5. We have 5/39. I'll stick it here because I don't have room. U over v du dv. Are we comfortable about essentially what I should call step 4, which is convert everything into u's and v's? You comfortable with that? Right. Once you get to here, forget where it came from. It doesn't matter it came from a Jacobian or whatever it came from. Isn't it just a double integral in 2 variables? One happens to be called u and the other happens to be called v. In this particular question, is it separable? And you know my rule about, well, it's not a rule, but you know my idea is if you can separate it, you should. So 4/5 of this guy. Do you know that darn 5/39s? Can I just stick it outside over there and that's it gone? And that means I can just do the 0 to 5 of the u du. Okay, at this point, can I just dot that? Can you imagine it's just going to be an ugly multiple of some logs, probably? I don't expect a pretty answer, but it will be the right answer. Now, why would we even need Jacobians? If you can imagine that this fella here looks something like that, if you were going to keep it as x's and y's, wouldn't that be quite difficult to describe this region as x goes from here to here? Because at different points, don't you get different start and finish heights? Can you imagine how difficult it would be to solve this integral if it was left in its xy format, right? The region is not a nice region, right? And if you do x's, if you try y's, it's just as bad. I mean, at this point here, it's that straight line to that straight line, and then that takes you to about here. But then once you go from here to here in this darker region, isn't it too different? Well, one of them's different, one's the same. And then at this point you change over and isn't this third region. So, I mean, the only way you could do it would be what, to split it into 3 separate integrals. And, you know, have a y equals x, whatever, to a y equals 2x plus 4, whatever it would be. And that isn't even the end. Then you have to do this ugly guy. Okay, imagine integrating this with respect to x and then with y, using very weird limits of integration and having to do it 3 times. This is cleaner, isn't it? This just makes the world that little bit simpler. Okay, so that's how question 1 and 2 are going to look like. And this is a version of question 3. So we're looking at this double integral, and this is the region. So when I look at the region in particular, and definitely here's backup, who would you pick as your U and your V based on what's in front of you here for question 3? Who would you choose?
U equals x minus y, v equals x plus y.
And does it matter which one you call U and V?
No.
Not one bit. Now, that is going to be good. I'm bring back my little guy here. Then won't this become U equals 0 to U equals 6? And won't this become V equals 0 to V equals 7? Do you know it has quite a lot of similarities to question 1, doesn't it? Would you agree that these are linear?
Yes.
So if I want to find this Jacobian, which I do need to find, can't I just do the cheat of switching places? Right. And then whatever number I get, take its reciprocal, and that's what this answer is. So partial with x and partial with y, partial derivative of v with x, partial derivative of v with y. And if you differentiate this with x, you get 1, and then you get -1, and then you get 1, and then you get 1. And I believe you get 1, take away negative, add 1, you get 2. So the Jacobian is a half. Are we cool with that bit? Agreed? Now, hasn't happened yet. Who knows, it might not happen in the few questions you got, but it will happen. Couldn't that be -2? And couldn't you end up with -2?
Yes.
That would be -1/2, which is true. But you stick an absolute value around it. In other words, Jacobians, which are numbers, should always be positive, right? Technically, all Jacobians should be positive, but the only ones that we really focus in on are the number ones, right? The ones that come from linear typically. So there's a half. That's what we use. Now you put this package together. This double integral R of 9 x plus y e to the x squared minus y squared dA, that's this guy, is going to turn into u equals, and there's no particular reason I'm putting u first, it's just what I saw when I wrote it down. V equals u is 0 to 7. 9. X plus y is v. Okay, what are you going to do about x squared minus y squared?
It's uv, right?
Yes. I don't know why I stuck the absolute value around it, but it's too late to change it. The Jacobian and dv and du. Are we good with this fella? Right, so what would we do? I'd probably pull out the 9/2 just because it's annoying me. Is this particular integral separable?
It is not.
Right, so we just have to fight through. Now, I just by the way my brain was working, I decided to do the V's before the U's. Now that I'm looking at it, do you think it might have been a better choice to do the U first and the V second?
I remember this from the homework and I switched it around, yeah.
Yes. So. And at this point, can I just dot it and you'll get some ugly multiple of e to the power of something. At least the particular Jacobian situations, the change in variable situations, they do have, if you do enough of them, don't they begin to have a flow, at least the linear ones? Right. So if there are no more questions on that one. This is 4. Now, there's 2 other questions after this now. It's just reduced down to 5 and 6. 5 and 6 are worked examples, so you get lots of clues, so I'll just let you do them. 6 you will like, Lindsay, because 6 is proving for a 3x3 spherical coordinates.
Nice.
So let's get started. Not as started as the others. This thing over here, shouldn't this thing over here be x plus y is 7 and x plus y is 9 and x minus 42y is 40 and x minus 42y is 7, right? It's none of those. It's 4 coordinates. So I guess the first thing I'm going to have to do is figure out, there's 1, 0. There's 8, 0. There's 0, 1. And 0, 8. And here is the region that they're talking about. So far, so good. Now, this region is, excuse me, I'm getting some stuff up here. Right. This region here is basically made up of 4 straight lines. This line here, which I'm just going to put some dots on, is going to be y equals, it's negative x, add 1, so I guess it's 1 minus x. And this line here is very similar. What is it? It's going to be y equals 8 minus x. I'm going to rearrange that a little bit and call it x plus y equals 1. And I'm going to rearrange this one and have x plus y equals 8. Well, that's good. That would be cool. Now, this side here is essentially x equals 0. And this side going this way, the side here, is y equals 0. And this side here, I guess I'll put it a little bit differently, is x equals 0. So this region is bounded by x equals 0, y equals 0, x add y equals 1, and x add y equals 8. So this is going to be a little bit trickier. We have to pick a u and a v, agreed? The x add y is a very good candidate. These 2 sides are not helping me one bit. But if you look at the guy I'm integrating, can you see there's a good clue to who the other one should be? Can you see the x add y? Can you see the other one up here? So I'm going to use that guy. Now, these are nice and these are linear, And that means I will be able to get this bit, step 3, done. What I haven't figured out yet is how to describe this region in terms of what U and V are doing. So that's where things get a little bit messy. Let's see what we can do about that. Well, let's take the easy part. Wouldn't you agree that this basically tells us U goes from 1 and ends up at 8? You happy about x add y is 1 and x add y is 8 is U equals 1 to U equals 8. So that means I can do a U equals 1 to U equals 8 guy. Actually, I'm not sure why I'm writing it that way. What we got a problem with is who the other two guys look like. And the other two sides are these two fellas here. Because they are going to be the restrictions on the V, right? We already know where U varies from. What we don't know is where V varies from. And we know that it's made up from this vertical and this horizontal line, but we have got to figure out how to make that happen. And so this one is kind of the ultimate horrible question. So if I write down my two guys again, U equals x add y, I'll call that equation 1, and V equals y minus x, which I'm going to call equation 2, I am going to have to turn these two guys into x as a function of U and y as a function of U and V. I didn't need to do it in any of the other linears, and if all I was looking for was the Jacobian, I wouldn't need to do it in this one either. But the reason I need to do it is because I do not know what these two lines are in terms of U and V, so I can get this. So looking at these two equations, I want to solve for x and then I want to solve for y. Think system of equations here. Actually, these are very nicely set up, aren't they?
Yeah, you could just add U and V to get rid of X, right?
Correct. Which means then that y is a half U and a half V. Agreed? And then if I put a little bubble around that so I don't lose it, if I then put y equals a half U plus a half V, and I put that into, I know, say equation 1, I should be able to find out what x is. So U is x plus y, and that makes x a half U take away a half V, so there's the x. Now you may think, well, what's the good of that? Well, actually, since I've done all the hard work here, couldn't I just do my normal Jacobian then? But that's not the main reason. I have two distinct boundaries that I need to work on. Right, when x is equal to 0, if you use it in this equation, what you've just said is a half U take away a half V is 0. Right? If a half that is 0, and I'm telling you that x is 0, then the relationship becomes that. If you rearrange this information, don't you get V equals U? Are we okay with that, guy? Now, how about y equals 0? Well, if I tell you a half U plus a half V is y, and then I tell you at the same time that y is 0, you get that relationship. And you now get this fella. So x equals 0 is the same thing as V equals U. And y equals 0 is the same thing as v equals negative u. So I don't think it should be too much difficulty to stick in a negative u and a u. Are you happy that the boundary of v isn't numbers, but it's between u and negative u? Right. What other pieces do I need? Well, I've now got region S, this stuff. I need to find the Jacobian. Well, in this case, I might as well just use the normal formula for getting a Jacobian. Because I already had to do the hard work in making it, might as well use it. If you take x, where is x? If you take x and you do it with u, you get a half, a negative a half, and you get 1/2 and a half, and you get a quarter, add a quarter, you get a half. I think that's all the pieces then. So the original integral over region R was 3 lots of the cosine of 9 times y take away x, y add x, dA is going to be transformed into the region S, which is from u equals 1 to u equals 8, and from v equals negative u to v equals u. 3 times the cosine, instead of y minus x, we have v over u. Instead of the dA, we have the Jacobian, du, dv. And that is the new integral. So I guess I could pull out that. It's not much help, but I guess it's better than nothing.
The 9 still needs to be inside the cosine, right?
Oh, thank you. I dropped it. There it is. Yes, you're right. It
Okay.
does. Okay, not the prettiest guy in the world, but would you agree that at least you could do it now? And there's one mistake that I just caught in time. You do v before you do u, right? Now you integrate that with v, plug in these two numbers for the limits on v, you'll be left with an integral in u's. You'll do the integral with u's and you'll use the numbers 1 to 8, and then times the whole thing by that awkward 3 halves that's floating around. And ... you'd be finished. Okay. I hope you feel a little bit more comfortable about the Jacobian, right? The change in variable method. This last one is kind of like the ultimate version of horrible, because of all the things that you had to do that you typically get away with in the earlier questions. Anything you want to ask or talk about before I move on? Okay, then it's time for us to start a new phase. Let's get this thing set up. Right. Just closing off for a few seconds. Let me check something else. I never find things when I want them. It is. I just wanted to check because I wasn't 100% sure. We are on our last chapter. Wow.
Wow.
That was fast.
Yeah. So, chapter 16. We're going to look at things called vector functions. We're going to look at things called, well, they have various names, and they're called vector fields. Better put that name in. What other names are they called? I know there's a few other names floating around in my brain. No, those are the two that are coming to me right now. Let's give you an intro before we start, even looking at the first section. If I said to you z equals f of x, y, we've been dealing with those situations for quite a while. An example of that could be z equals x squared minus 2xy plus e to the x, right? Whatever. When you look at all the points in 3D space that this is true for, don't you basically end up with surfaces, right? It's the skin of a rolling hill, or if you do an example like this, for instance, don't you basically end up with a sphere, right, in 3D? But it's still the surface, right? So what we're talking about here are all the points in 3D space that have the property that when you square their x, y, and z coordinates and add them, you get the answer 9. In this one here, we're looking at all the points in 3D space that when you square the x and take away this and add that, you get the z coordinate of the point. And what have we done with these things? Well, we've integrated them, haven't we? And we found partial derivatives for them. And basically, that's what calculus does, doesn't it? You take derivatives and integrals of things for reasons. Depends on how many variables are going around. We do double or triple integrals, right? And we've even changed variables, which is what Jacobians do, mostly for double integrals. But there's a new guy in town. It's a vector function. It's a vector field. These guys are scalars. What that means is that they're numbers, right? And isn't the number that you put in here generates a z coordinate number, right? They are single dimensional objects, right? Called scalars, numbers. A vector function is not the same thing. In fact, a vector function, as its name implies at least, has something to do with vectors, which means that your answer to what you get when you plug in x and y is not a number. The answer you get is a vector. I'll show you what a vector function looks like. Do you notice there's a big arrow floating above the f? That indicates that this is a vector function, right? A vector field. If you are doing them in textbooks, you won't see that arrow. Does anybody know what the convention in textbooks is for when things are vectors?
Do they bold them?
They bold them, right? So be careful, because when you look at it and you're not paying attention, it'll just look like him, right? Well, whatever. Right, it'll just look like him. Well, not quite the same, but you could forget it. This is an example of have you noticed that it uses vector notation? So for any given point in 2D space, this is the vector that you would generate. You can also have it written down like that. Now, what did earth does a vector function help us model? Well, imagine that you're talking, this is a 2D vector function. You take any point that you like. Let's suppose I choose the point 1, 2, this point here. If you plug in 1 and 2, what do you get? Well, the vector function at the point 1, 2 is 3 times 1 times 2, which is 6, and 4 times 1 squared, which is 4. And can you imagine at that point that you do a vector which is what, 6 along and 4 up? You do a vector that looks something like that. And for every single point in the universe, for instance, if I did the point 0, is that a good choice? Yeah. Let's do the point -1, 0. Well, the value of the vector function at -1, 0 is 3 times -1 times 0 and 4 times -1 squared. So it would be the vector 0, 4. And what does that look like? Well, you don't go anywhere and you go up 4. Can you imagine doing lots and lots of different points in 2D space, and for every single one of these points, you found out what the vector would be at that point? Now, you would probably get some really weird vectors going all sorts of places, right? And some would be really long, and just because of the way things work, some would be really small. So if you're going to visualize a vector function, what I want you to think of is, think of wind. Right? Can you imagine it in a storm at any given point, like in a cyclone or if you looked at one specific point, wouldn't it be a wind direction? And if the wind is really strong, wouldn't that vector be long? And if the wind is kind of gentle and calm, won't that vector direction be quite small? Can you see that you could use this to model fluids, currents, the wind, magnetic lines? I'm not sure what they're called now, right? It's very good at modeling. Say the word?
Lines of flux.
Lines of flux. Actually, you are going to find out in this section how to calculate a thing called flux. So I'm glad Christopher even heard that name, because you're going to tell the rest of us what the heck it is when we calculate it, because we just, in maths, show you how to do it. So there are some conventions that they typically do, especially in software, because nobody in their right mind is going to draw one of these by hand. Can you imagine how much work it would take if you had, say, 100 dots, and each one of them you had to calculate a vector for, right? And then you had to try your best to draw it. So what are some of the conventions? One of the conventions is that theoretically, you can actually find the vector function at any number, not just whole numbers. Can I find the vector function at 0.1, comma, nothing, 1, 2, 3, 4, 5? So what we tend to do is we only evaluate them at little snapshots. That's the first convention. And then the second convention is that the software does not normally draw the vectors to their full extent. You normally draw little baby unit vectors. So what you get is the idea of the direction that the vector is in, but not its magnitude. And so you might get a guy that looks something like this.
Is that a direction field?
Yes. Have you heard of them?
Yeah, I remember them from differential equations.
Yes. Direction field is another name for these guys. I'm fed up drawing this, so I'm probably not going to draw any more of them. So can you imagine then that what this here is modeling is like a wind pattern, or maybe the current on the, the surface of a river and how things are moving. And you can imagine things traveling through them, which is what they use them for in differential equations. But we're going to use them for much more, well, not more interesting things, but we're going to use them for other things as well. So this is what a vector function looks like. Your function generates vectors in 2D, and these vector fields, these vector functions, allow us to model dynamic situations, right? Things like magnetic fields. In fact, anything in physics or chemistry that has the word field tagged on at the end is probably going to get modeled using a vector function vector field. So force field, magnetic field, can't think of any others right now. Velocity field, I guess if you had the wind moving, it might be called that. So if you see the word field at the end of something, there's a very good chance that they're going to use this kind of math to model it. So wouldn't it be nice if you didn't have to do what I had to do, and there was a piece of software that would do it for us, right? Do you think there is such a piece of software?
Yes.
Yes. And if there wasn't, I would be telling one of you, go and make one, please. So there's definitely a demand for it. So I'm going to try and find the darn thing now. And have I got the right one here? Probably not. Okay, I'm going to, for the last few moments, you want to say hi while I'm doing this, because we only have a few moments left. And I don't want to use up your valuable time. Okay. Okay, here we go. You should be looking at my Canvas page. Is that what you're saying?
Yes.
If you click on the vector field 2D, this will give you a 2D vector field. There we go. Essentially, you put in here what you want to be the first guy. So in my case, what was it, 3xy? And then in here, you put in what the second one was going to be. In my case, it was what, 4x squared?
Yeah.
And then you click off it, and there is the vector field. Now, this one is actually slightly better than what I said. It's not uncommon for all the vectors to be the same length, but in this case, they've been kind of clever. Do you notice that the long ones are really long and the short ones are really short? So not only do you get an impression of direction, don't you also get the strength of that particular vector, right? The longer it is, the bigger it is. Now, this is a pretty cool looking vector field. Now, I should be able to play about with it a little bit. Okay, that's not a good way of playing about with it. That's probably not a good way. There. If I'm looking at this model, I'm trying to think of wind. I always like, my analogy is always think, what would a very weird windstorm look like? And this is what they're trying to describe. Would you agree that at the center, there's almost no wind at all? And then as you move out of the center, isn't there a kind of explosive in all directions kind of thing? Like, actually, I take that back. It's zooming out the way here, and it's coming in from here. Oh, okay, here's my hands coming. Wind is coming in this way and slowly dissipating to nothing. And then it hits the center where nothing's happening. And then somehow or other, it builds up force and it shoots out like a big X. And on the edges, it kind of just doesn't go near the center. Do you see on the edges, it's curving around like that? So this would be, you know, an object coming in, an aircraft flying in this wind. if it didn't have enough power and it let just let nature take its course, this aircraft would come in and it would get blown like that. Maybe try a different. How about a water current analogy? If you are on a little sailboat and the wind blows you, can you see that you're probably going to go like that? If you come in this way, aren't you going to get blown? Well, I'm not quite sure what's going to happen here. You're going to get becalmed. And yeah, I'm trying to think of analogies. It's a kind of cool thing.
Yeah.
Let's try one more. Let's try a guy with square roots, because they like square roots in these things. Okay. And let's do a kind of symmetry thing going on here. Okay, so I may have to tweak some of these because these vectors are too small to see. Oh, I like this one.
Come onto the page.
Say again?
Oh,
G?
sorry.
That's
So
okay.
they come into the page.
Yeah, it's still 2D, this one. There are 3D ones, and we'll probably show you them tomorrow. I'm sure I will. But this looks to me like there was an explosion at the origin and everything just shot off away from the center. Is that what you kind of say? That, right? And then it went. So you could, this would be quite a nice model for a very simple explosion. Not so sure why, but aren't all these vectors the same length? From what I can see. So that's probably a function of the x squared plus y squared. Because I'm 99% sure that if you looked at this vector, it's a unit vector. And so all of those vectors are 1 unit long. Kind of interesting. What would you think would happen if I stick just this fella here? Oops, this fella here. Get that one right. And I did just one change. I made it negative. What do you think might happen to the vector field?
Flip direction.
That's quite a major change to the pattern. You agree? Not quite sure what that is telling me. It's a bit like at the origin, there's a place you can't go. Do you see that as you try and go up here, don't you get bounced off it?
Unless you're on the y-axis.
In which case well, actually, if you're on the y-axis, you get sucked in towards it. And if you're on the x-axis, don't you get shot away from it? I just thought of a really cool model for this. If I turned this into a 3D one, couldn't we model the forces near a black hole? In a 3D way, which is what black holes are. That'd be a cool. I'm sure the model is very much more complicated, but at least I do a decent one. You could do a gravity well pretty easily on these as well, if you know what a gravity well is. Right, I have kept you long enough. Sorry for taking you over time, but this is cool stuff, isn't it? It's visual. I love visual. I'm useless at drawing it, but I do like it. So I'll hang about. You may or may not have some questions that you want me to go over, and that's what I'm here for. I do charge $14 an hour, so I should put that warning up. Oh, I've got a lot of people. Okay, who wants to start the ball rolling?
Professor, could you please?
Sorry,
Oops.
G.
Okay, G, go for it. What you got?
I was saying, could you please release the test so that we can see it?
Oh, that's easy done. I'll just take a note. Yep. Do you want me to do it right now?
If somebody else has another question, they can ask.
You got a question while I'm thinking about this?
No, I mean that was.
Sorry, you go again, G.
Yeah, this is one of the problems with
I'm done.
Zoom is that you
I'm done.
don't
Go
get
ahead.
any physical clues to what the heck's going on, which is really frustrating for, for interrupting, which you don't mean to do, but you can't help it. Okay. Darn it in space, I am not on the right page. Right, what was your question going to be, Lindsay? I think I'll have to do G's later. It's not as easy as I thought it was going to be.
I would like to go over one of the questions from the test, the one about using cylindrical coordinates to find the volume of a solid between z equals x squared plus y squared and a sphere.
Okay, let me find that's test 3.
I think it's number 4, and the specific thing I had a problem with was finding the range of R. Okay,
so I'm looking at it. Well, I'm not looking at it because I'm in test mode. I don't want to be in test mode. I want to see the question. Okay, I could look at your question because they generate different ones for different people. So let's see your particular one. And question 4, you said?
Yeah.
Right, now z equals x squared plus y squared, and x squared plus y squared plus z squared equals 2.
Yeah.
Okay, so let me skip over to the screen and see we can figure out what those two guys look like.
So I know that x squared plus y squared is sort of like a rotated parabola, I guess. It's like a parabola rotated around the z-axis.
Yeah, they either look like this or they look like that, and the z-axis goes right up the center. Great.
Yeah, it opens up, so the top one is correct. So I know that's the thing, and I know there's a volume enclosed between those two. Like,
right.
Okay, so that one has its minimum at 0. And then x squared plus y squared plus z squared is a sphere of radius 2.
Correct.
And so I know that I know what it wants is the volume enclosed between them, but where I got wadded up was trying to figure out the range for R.
Okay, so if you take this fella and you rearrange him, you get that guy. Agreed?
Yeah.
And that guy becomes that guy. Agreed?
Is that okay when we're in cylindrical coordinates?
That I find Z like that. And what's the other fella going to be? It's going to be what, R squared? So you're try to think of what your question is.
Well, I mean, is it okay to just be like, okay, because in cylindrical coordinates, I thought it was like x squared plus y squared plus z squared was our
No,
R.
that's spherical coordinates, and that's rho squared.
Did I mess it up that way?
Yes. It looks to me like that's what you did.
Oh, nuts. Okay, so then it would just be r squared equals root z minus r squared. Okay, and so then it would be r to the 4th equals z minus r squared.
And does it all flow from there?
I will look at it because I think it might.
Okay.
Yeah, I know the homeworks are very so I had the same issue during the homework, trying to figure out between spherical coordinate and the other ones.
If you want to know the range in Z, the range in Z is r squared on this side and 2 minus r squared on that side. And the others are, in your case, I've lost the darn thing, but in your case, what are we looking at?
Oh. Okay.
Right
so
now,
that's what
you still have some work to do, because these two shapes, that's this one and this one, they intersect. And
Right.
so you
So
have
it
to.
was the intersection point that I think kind of got me. Like,
Right. Well, if you take this thing and that thing and let me start again. I want to find out where this guy and this guy intersect. Okay. So what do I know? Is I know that this thing here says z equals r squared. So that's just the same information. So I can call this z equals r squared. And this is z squared, so this is r to the 4, and this is going to equal, in this case, what's it going to equal? It's going to equal 2. And now I have this, and that can be factored as an r squared and r squared, plus 2 here and minus 1 here. I think that's right. Okay. And when we solve, you get no solutions here. And here you get 2 solutions. But that one's no use, so r equals 1. And you get r equals 0 to r equals 1, which you could probably have figured out. But when the two things intersect with each other, they make a circle. At least when you look at it from above, it looks like a circle. And it happens to be a circle and with an r value of 1. If you're looking at your z values, we already set them up. I've got them in front of me here. That's an r squared and the 2 minus r squared. And the only guy that's actually not a real issue is that guy. So that's the major piece of what you needed.
okay.
So the intersection of the two was awkward. Now, that's just one way of looking at it. If you want to turn them into x squared plus y squared and replace this guy with x squared plus y squared, you do get a really, really ugly equation in x's with squares and 4s, which is really hard to solve. And you don't really want x's and y's anyway, so it would be a good idea to replace this, and so that this becomes just an equation in R. And that was the algebra trick to find this fella.